In this video, we're going to take the last step in working with our guitar sampler sound. So this is our earlier example of a guitar being plucked once at a particular frequency or a particular note. And what we see when we look at that, and to make our lives a little bit easier, we're going to limit ourselves to exactly 4 seconds as the length of this signal. We saw that at this full 4-second span, it's really hard to see what's going on. Things are happening at very high frequencies relative to what we can see here. So if we zoomed in, we saw this kind of graph in our earlier work. Now that signal, we said, could be decomposed in principle into a sum of coefficients times our e to the I, and it was a kt in principle. However, when we want to have a 4-second long signal, basically we want our functions to repeat precisely and end after 4 seconds and go back to the start, we called that length L. And to get the natural complex exponential to repeat itself, it's exactly like sine and cosine. We put 2 pi over L inside there as a multiplier, and that guaranteed that after 4 seconds, if L was 4, we would get back to where we started. And in principle, we would add up an infinite number of these, so k would go from minus infinity to infinity in this series. So in principle, this is what's doing the oscillations, and the ck's are what we want, because those tell us how much of each frequency is present in this complicated signal. Well, there was a technique for finding those, and that was fundamentally to take a dot product or an inner product between the function that we have, this signal here, and these functions here. So it's a really nice mapping. We're reusing the function we have in our series as one of the functions in our building blocks. And there's tons of nice linear algebra that goes with that. The fact that this is an orthogonal set means we can do projection like dot products like we'd expect. The only caveat is we have to make this a unit function, length 1. To make all of this work out, we would divide usually by 1 over 2 pi. Oh wait, but we've changed the period, so we've squished that a little bit, and we divide by the new period L. That will guarantee that we're getting the right scaling for these functions here, which aren't, unfortunately, magnitude 1. But aside from that, think of f of t and this as a dot product, basically saying how similar is this to this. And actually, when we get to the next stage here, we're going to see a dot product naturally arising. If you're feeling a little skeptical or still trying to struggle with why a dot product, what does that mean here for functions? And the reason that's going to show up is because we don't actually have this situation. We have this situation where we have discrete data. Looking closely, we actually have points in an array in Python, and that is not quite analogous to the continuous regime here. Why does it matter? Well, because this inner product that we have here would actually have been computed through the definition of what we mean by those angle brackets as an integral of the function f of t times e to the I 2 pi over L. So this function here, 2 pi over L, kt dt, with one extra little caveat. It's supposed to be f of t, and we are in a complex number world here, so for reasons we won't belabor right now, but just to make things work in a linear algebra sense, we need the complex conjugate, and it turns out for complex exponentials, that just means sliding a negative in here. You can go back to Euler's formula and see how that would work its way out. And the last thing is this is a definite integral, so it has to be start and end points. So over this entire length of this series, we're going to integrate this function against first sort of think of it as a cosine curve that does 1 cycle, then a cosine curve that does 2 cycles, and 3 cycles, and 4 cycles, and so on. And the problem is we can't calculate this integral if we don't have a formula. What do we do if we have discrete data? Well, think about how we got to integrals in the first place. Back in first year calculus, we covered integrals as being the result of taking a limit of smaller and smaller delta t's and adding them up, or in this case here, we're going to have a sum instead of integral. Instead of dt, we're going to have delta t's, and then we're going to hone in on what goes inside. Well, the f of t is actually just f at specific instances. We already are using I, so we're going to need a new variable here. I'm going to call it little n, and I'll explain that in a second. So we're going to take the function at a specific point, that is measured in our data set. And then we're going to multiply that by e to the negative I. Nothing changes in the integral, remember? It's just being careful about what you mean by all these terms. In particular, we need the k still. But the t is going to be these discrete times. So it's going to be t sub n. And so we definitely need to move this delta t further back out there. So this integral, area under this curve, if you want to think of it as that, can be computed or estimated by taking the area under these dots using the function value of these specific points, these discrete points, and then this exponential evaluated at those same discrete points. And we still have the 1 over L, that wouldn't change. And just to formalize this, we would have a sum over all the data points. So I'll frame this out here. Our x was a vector that had a bunch of data in it. The x covers this entire 4-second interval. This is just the zoomed in, so imagine starting a bit earlier and going a bit later. It's associated with indices 0, 1, 2, 3, 4, all the way out to, well, actually that's going to be an issue. We have to find out how many data points there were in here, and that's going to depend on our time values. So our times, these tn's here, are 0, and what's the next time point? Well, we had a sampling rate as one of the ingredients here. I'll put that in a second, but we called it SR in an earlier video. And each step we take in the time values is one sampling rate later. And just a reminder, this is for standard audio formats. We had a sampling rate of 22,050, and that had units of hertz, which will help us understand some of the ingredients here. So to make this concrete, if we have 4 seconds of sounds, and this is the sampling rate per second, we're going to have 4 times this, which will be 88,000, 4 times 50 is 200. The only caveat we have to keep our minds on is that there's this annoying intervals versus points. If we have this many intervals, then there's one more point to go around that. I just want to do a quick sketch here. If I have 3 intervals, I need 4 points to get that 1, 2, 3, 4 versus the 3 intervals 1, 2, 3. So there's always this off by 1 issue that's going to come up. However, if we just keep that in the back of our minds for the moment, here we would have all these numbers that are associated with all our x values and the matching time values, with the last time value being 4. I'm just going to move this down so they don't conflict and get in each other's way. This becomes something that we can compute. And even more relevant to us when we get to the coding, well, the function values at tn, that is exactly what we meant by x. In fact, if we use Python notation, x at the nth point, so little n, 0, first, second, third, fourth, imagine a loop going through those to make this sum. And second all here, if we made this tn actual array, we would have tn. A fun thing to note is once we get to this point, and if you look at what the calculation's doing here, we're adding up the first element of x times the first element of t modified, but then the second element times plus the third element times the third element. Oh my goodness, that's a dot product. So this crazy integral looking thing here, when we break it down into discrete chunks, is exactly a dot product. This is the vector x, our 88,201 elements here, dotted with e to the negative I 2 pi over all this junk. The key thing is it's with a t inside of it. That t is a vector. So we have this t of the same length. Let's highlight that in color here just to be absolutely clear. We have the x vector being dotted with adding up element by element multiplications of these transformed time vector here, but it's still going to be a vector in its final form. So that to me is exciting. That provides a rationale for this crazy, why am I taking integrals of things and what? Well, because dot products, when appropriately built out, are equal to these kinds of integrals. Now we're just going to remove that as a nice interface or concept idea. It's great, but it clogs out the page a bit. What does this get us to? Well, what we really want at the end of the day are these CK values. Now, there might be some other fudging around coefficients here, so we're just going to go for the principal because I'm not going to ask you to calculate the CKs by hand. This is our time domain information. We had our x vector, that was actually our signal. And with that we had corresponding counts in different sizes or different strategies. One is strictly an index count, and one is the actual time values that go with the parallel measurements. So that involved our sampling rate. What we then calculate through this transformation is we get a vector of c's back. And if you take a careful look at that series there, well, it's ck's, so let's index by k instead of by n. So it's going to have k being 0, 1, 2, 3, and so on. And it ends up being all the way out to 88,200. And these numbers here end up being complex numbers. So I'm just going to emphasize that here. Try to take one of them. We're going to have an a plus bi, and then another one, and then another one. 88,200 and one of them along the whole length there. What we really want to know, though, is what frequencies those are associated with. So we're going to do a little sidebar here, just reminding you about the frequencies. If we have sine of t, the frequency for that is, well, remember it's in hertz. Frequencies we're going to list in over time or over seconds. And it takes 2 pi to complete one sine cycle, so it's 1 over 2 pi. And so sine of 2 pi t, multipliers in here, multiply the frequency. That just gives us the nice perfect, well, not perfect, simple unitary oscillations at 1 hertz. And if we had sine of 2 pi over L t, the frequency is, well, we just divided by L, 1 over L hertz. Of course, I'm just a hair short there, hertz. And that's exactly the same as our exponential, except actually our exponential had one more thing in it. It had a kt in there, so let's slide that in now. Kt, and so if we have another k in there, it's going to be k over L hertz. And that's the same for our e to the I 2 pi over L times k times sine, and these exponentials have exactly the same frequency because of Euler's formula breaking this down into that same sine function. So that has a frequency of k over L hertz. Okay. Well, that means that each k comes with its own frequency, and the c that goes with it is how much of that it's the frequency in the magnitudes. There we go. So our frequency, let's call that, we've already used f, we're going to call it frequency here. We're going to have a matching set of those, and let's look carefully at this. When k is 1, it's going to be 1 over, sorry, k is 0, we always start with 0. There's a 0 frequency there. That's, in fact, a constant term that blends into this. But when we have 1 over L, when k is 1, we'll have 1 over L. When k is 2, we'll have 2 over L. And then we're going to have 3 over L and so on. And at the end, we'll have 88,200 over L. Just tidy that up a bit. And there's a fun little realization at the end here. This number is, for our example, when L is 4, this is 88,200 divided by 4. Well, if you divide that out, you get 22,050. Well, that's exactly our sampling ratio, or sampling rate. So this last value is our sampling rate, and so we have a sequence of linearly spaced frequencies from 0 up to the sampling rate, with n equal to L times the sampling rate. The 88,000 came from sampling rate times 4 plus 1 elements. Okay, a lot of math on the page. Take a step back. Why is this going to help us? So far we had all of this. Let's see if I can draw a circle around this. We had all this in our code earlier when we first started using Python with the guitar sample. We had the n's, the t's, all this stuff, and in fact we plotted the x against the t, and that's what gave us this graph here, or zooming in gave us this graph here. That was time against x. Then we ran some Fourier transform thing, and we got some stuff, and we weren't sure what it meant. Well, what that was is all these c values here. Now we have the extra layer of knowing what those represent. What we're going to end up doing now is plotting that see against that frequency. And there we're going to see when we pluck a guitar at a certain pitch, we are going to get oscillations of high oscillations, high amplitude oscillations at very specific frequencies, and that'll be how we interpret the Fourier transform. It will be a look at magnitudes against frequencies, and we can interpret that as how the sound is made up of basic building blocks of sines and cosines.